Okay, so let's look at some data processing with errors and uncertainty, and we're going to look at the effect of temperature on the rate of reaction. So the speed actually runs fairly quick here. This is just the basic data entry. I'm going to do this in Google Sheets. It's the software that you're going to always have access to. I'm going to show you some addressing and just some how to manipulate some formulas, that sort of thing. So you'll notice that up near the top I left some space before I started making a data table. I'm going to put some constants and things up there, cells where I'm always going to want to come back and get some values from. So in B1 I wrote the 273, which is the conversion from Celsius to Kelvin. Notice I put temperature in Celsius, temperature in Kelvin, trial 1, 2, 3, and the times. I'm putting the units there as well. You would eventually also want to put the uncertainties in those headers. I haven't yet, and I don't actually in this video. If this was a formal type report, you would want to do that though. Alright, so in A2 I'm going to write concentration of sulfur to obscure the X, and then I'm going to put the actual numerical value, no units or anything like that, in cell B2. Right, I'm going to use that text wrapping feature. What that does, that actually the text doesn't overflow from cell to cell. You can see it just bundles it all in one and expands the cells. So here are the temperature values that I'm working with. I'm going to use what's called an absolute address right now. As you can see the little note there on the screen. Basically, I'm telling it to handle the conversion. Always go back and get that 273 number from that cell B2. So now I've got all my temperatures in column B in Kelvin. Right, and I'm going to go enter my raw data for all of my times in the respective columns. Okay, so again, go back, pause that video, see what I'm talking about, the relative or the absolute addressing, that sort of thing, versus the relative addressing, and just try it. Right, I'd set up a spreadsheet and do it the same way. Okay. So, reasonable time uncertainty. Okay, I'm making a note of this here because, quite frankly, I know the stopwatch is displayed to the hundredths of seconds position, but the absolute best uncertainty we can hope to get is 0.1 seconds. That's just shown through many experiments. All right, and that's a human limitation. Okay, so make sure that all of your times, if you ever do any rates type work, that you are reporting just to the 0.1 of a second. Okay, so then average time, you're going to average the three values, add them up, divide by 3. Okay, adjust your significant figures accordingly. So again, you can only at best hope to report to the 0.1 position. Okay, so rate of reaction was the concentration found in B2, and it's going to be divided by the time. Okay, so there's my rates for my different temperatures. So it seems to make sense, kind of agrees with collision theory. Temperature gets higher, kinetic energy increases, rate increases as well. Makes perfect sense. Okay, now there is a temperature uncertainty as well. The thermometers that you used were divided into degrees Celsius, so it's half a degree Celsius, which is half a Kelvin. Right, so you can see how I built the uncertainty into the header there, just to show you what to do. I'm going to show you how to bring those uncertainties into your calculations. So in order to do that, I've got to move some things around. So to move an entire column, so to move my rates column, I'm going to cut it, and I'm going to paste it into a new column. If I use the Control X function on the keyboard, all right, I actually move the whole thing, and all the formulas that I've used are rewritten for me. Okay, so now to get the uncertainty in the time, alright, I'm going to use the half range method. So I'm going to take the largest time, I'm going to subtract the smallest time, I'm going to divide by 2. Okay. This is our preferred and accepted method of getting the uncertainty in an average, rather than just saying it's 0.1 seconds or dividing it by 3. That type of operation doesn't make sense. Alright, so the reasonable approach is to say that it is some compilation of the largest value and the smallest one. So again, it's a manual operation that you've got to do here. Take your longest time, your shortest time, subtract them, divide by 2. Alright, now again, absolute uncertainty is kind of no good to me, so I need to convert that to a % uncertainty. What do? I take the absolute uncertainty in the time, So that would be found in column G, and I divide that by the actual measurement of time, which is found in column F. Right? So now I just drag the formula down, that's relative addressing, and it divides column G by column F each time. Multiply by 100, there's a percentage. Okay, I'm also going to get the percent uncertainty in the temperature. Same idea. Again, don't forget, you can always stop this video, go back, pause it as necessary, work through this yourselves as well. Make sure you can do this. This is the level of treatment that is expected in IA. Okay, so now I'm going to do something that I kind of make a judgment call on this one because IB doesn't really like to specify how to handle your uncertainty in a final answer in chemistry. I'm going to say if you've made a graph and you are able to get the percent uncertainty for both X and Y, it's much easier to interpret that data if you combine them. So I add my percent uncertainty in my X to my percent uncertainty in my Y, and I come up with this total uncertainty column. It's not necessarily standard practice beyond IB, but it has been accepted by the IBO. Alright, I would go through and I would adjust all my significant figures if I was submitting this. Alright, I didn't here. Alright. When you start to study physics and bio, you'll learn a little bit more about error bars. I'll do a little bit of treatment on that. It would be possible to actually do X and Y error bars, but my combination of the uncertainties there is to eliminate two different sets. That'll make sense later on. Okay, so I'm going to make a graph. I'm going to say, alright, what was the purpose of this? I wanted to see how rate changed with temperature, so let's do that. Let's relate the two variables. Alright, so I'm going to have temperature on my X. I highlight the temperature in Kelvin column, hold Control, then highlight the rate column with my mouse. Okay, so I can see I get what looks kind of like a curve. Those first 4 points sure do look linear to me. Alright, so I can run a couple different fits on this. Alright, I'm going to go through and I'm going to title my graph. I'm going to title my axes. Alright, I may want to put a legend in or take it out. You can see that I took the legend out. I'm going to put it back in a second because I won't get the actual equation to display without it. You can see there's an error bars function in Sheets, but it doesn't do what it's supposed to do. Alright, it doesn't have the power of Excel, so there's another program that we need to sort of borrow some functionality from later on. I'll show you that in a separate video. Okay, so here if I put a linear trend line through this data, I see it's an okay fit. Right, I can throw an R² value on here and I get 0.94 or something like that. So it's not great. I mean, ideal fit is 1. So this is not the greatest. Alright, so I may want to see, well, it looks like it's curving up towards the end. So what if I try to put an exponential function on this? Alright, now I will say theory would actually predict that this relationship should be more exponential than linear. Alright, so I am going to leave the exponential curve on there instead. Alright, but this is the idea behind what we'll later show using error bars. Is the error bars allow us to say what is a reasonable fit for the data without just relying on the R² values. Alright, so I typically move my graph into its own separate sheet just so I can work with it. Alright, but now again, what do I want to do here? I was looking to see how rate was influenced by temperature. So rate of reaction, remember, if I go and I look at the rate law that we developed for this process, alright, the rate was equal to the rate constant times the thiosulfate concentration raised to the first power times the hydrochloric acid concentration raised to the 0th power, so that term didn't matter. So really, rate was directly proportional to the concentration of thiosulfate. I've held thiosulfate's concentration constant here, so when I changed the temperature, what must have been changing was the rate constant. So what I really want to look at here is how the temperature affects the rate constant. Alright, so what I'm actually going to do is I'm going to put another column in here and I'm going to compute the rate constant. How do I do that? Solve for K. That means take your rate, divide it by the concentration of thiosulfate. So I'm going to put thiosulfate's concentration in a box here. Alright, I'm going to write 0.1. So now I'm going to use that absolute addressing function again. So I'm going to say go take your rate, which is found in J10. I'm going to divide it by $E, $3. That's going to tell Sheets to always go back and divide by that 0.1. here's my rate constants. Note they're the unit of the rate constant. You can have a look and figure out why it would be 1 over seconds. Okay, so how does it change with temperature? I can make use again of relative addressing. I can say, alright, well, go find temperature. Alright, I could type rate constant in here and then manually type the values for the y, or I can just say equals, tell it where to go find those values, copy them in. Alright, I'm going to highlight this and put a loose chart on there. See, that's a curve. That's a pretty good curve on there. The issue that you're going to find is that this data is typically a curve. It's exponential. This is where we get into the Arrhenius parameters, all right? And this curve needs to be straightened, but it's not by doing a process that you would necessarily think of off the top of your head. We need to plot the inverse of temperature against the natural logarithm of the rate constant, and out will come a linear relationship from which you can compute the activation energy.